Very good morning. My name is Komal from BSc Second Year Chemistry Honors. Now I am reading a chapter Chemistry of Actinide for Visually Impaired Student. Let's start the chapter. Actinide constitute a series of elements following actiniums in the 7 periods of the periodic table. Actinide belong to F block as these are formed by the gradually filling of FF5F subcells. We have discussed the chemistry of lactinide in the previous chapter. Lactinide, which follow lanthanums, their atomic number is 57, involve the gradually fillings of 4F subcell. In this chapter, we will discuss the chemistry of another series of 14 elements which follow actinium. Atomic number have 89. This series of 14 elements is called the actinides. Actinides along with lanthanides constitute complete F block element. The endings IDE in actinide is not appropriate because it more correctly means negative ion such as oxide or chloride. Actinides were also named actinones by a group of scientists. However, the endings "ons" is used perfectly for non-metals such as boron, silicon, etc. Where all the actinides are distinctly metallic, IUPAC has now reclaimed these elements to be called actinoids with the ending OID rather than being called actinide or actinones. However, it is unfortunate the people still call these elements by their earlier name as actinides. Before World War II, the only naturally occur actinide, namely thorium, plutonium, and uranium, were known. Uranium is the heaviest naturally occurring element. It was after World War II that the remaining elements were artificially discovered through nuclear reaction. These elements are named man-made or synthetic elements. Another name coined for these elements is transuranic element. Transuranic elements are elements that have atomic number greater than 92. Let us now discuss the interesting aspect of the chemistry of actinide. Position of actinide in the periodic tables. An inspection of the periodic table reveals the electronic configuration of noble gas random as xenon have 54 atomic number, 6s2, 4f14, 5d10, 6p6 is a electronic configuration of actinoid. After random, the 7s and 7p orbital gain stability relative to a 5f orbital because s and p orbital are more penetrating than the d and f orbital. As a result, the next two electrons are being filled in the 7s orbital, which make the appearance of new element francium. Francium has 87 atomic number and radium have 88 atomic numbers belonging to S block of element. After the addition of two elements in the random core, the 5f and 6d electron penetrate the 7s orbital. The least penetrating f orbitals are stabilized on account of the increase in effective nuclear charge outside the next noble gas core with increasing atomic number. As a result, the next 14 electrons from thorium have 19 atomic number to Lithium have 103 atomic number enter the 5f cell. It is important to note that around actinium both the 5f and 6d subcells possess almost similar energies. Because of similar energy of 5 and 6d subcells, the incoming electron may enter either of the two subcells, which result in the uncontained of the electron configuration. As a result, it is doubtful whether the electron enter the 5f orbital or not. For example, the configuration of thorium has 90 atomic number may be written as either 5f0 6d2 7s2 or 5f1 6c 6d1 7s2. However, once filling starting in 5f orbital and 5f subcell becomes more and more stable. As a result, from uranium onward, the 5f cell becomes more stable. Thus, all the incoming electrons start filling, progressing in f orbital. The general electronic configuration of actinide can be as signed Rn 5f0 to 14 6d to 0 to 1 7s2. General characteristics of actinide. Some of general characteristics of actinide are detailed below. First is electronic configuration. As already discussed in section 5.1, the actinide involves the gradually filling of 5f subcells. The electronic configuration of titles actinium has 89th atomic number is Rn 6d17x1 have electronic configuration. Thus, from thorium onward, the 5f subcells start progressively filling. The general electronic configurations of the atom of actinide in the ground state may be written as Rn 5f1 to 14 6d0 to 1 7s2. The detailed electronic configuration of all the elements are present in tables. Name of element actinide denoted by a symbol Ac have atomic number 89. Quantum number of n quantum cell n is equal to 5 is SPDF. S have 2, P have 6, 9 have 10, F have 0. Next, n is equal to 2. Electronic configuration is Rn 6d1 7s2. Thorium have electronic configuration 6d1 7s2. Potassium have 6d1 7s2. Such that second property is a physical property. Some of the physical properties of the actinide are presented in table 5.2, which are discussed below. Melting and boiling point. The melting and boiling point of actinide are moderately high but are lower than those of a transition element, and infections of the table 5.2 reveal then that there is no regular trend in the melting and boiling point of the non-actinides. Element AC have 18.817 melting point and 2417 degrees Celsius boiling point, and 10 gram per volume have density 1.12 astronomical have radius, such that theriums have 1750 melting point and 4850 boiling point. 11.72 gram per volumes per centimeter volume have density and 1.08 have radius, such that density thirds. An infection of the table 5.2 reveals that the elements near uranium have very high densities. Americium resemble the corresponding lanthanoids. Europium is being less dense than it is neighboring. Fourth, ionic radii and actinide contraction. The size of the actinide's ion decreases regularly along the actinide series. This is because with increasing atomic number, the extra charge on the nucleus is purely screened by the F electron. The steady decrease in ionic radii with the increase in atomic number is called actinide contraction. A comparison of a M3 ionic radii of a actinide with those of a lactinide reveals that the actinide and lanthanide ions are very similarly in size. As a result, their chemical properties are also similar. The decrease in the ionic radii of M3 positive and M4 positive ions in case of actinides shown in figure 5.2. It is interesting to note that there is a decrease in atomic radii from thorium to uranium, which may be due to the increase in the most stable oxidation state from +4 to +6. In other words, the metallic bondings from thorium to uranium may be considered to consist of Mn plus ions with a total of n electrons for atoms. After plutonium, the metallic radius increased significantly again, which may reflect the increased lanthanide like behavior of the latter actinide, in which perfect oxidation state is +3, with only 3 electrons per atom available for metallic bonding. Oxidation state. The actinide elements show a greater range of a oxidation state than the lanthanide practically in the early part of the series. The different oxidation state of actinide element are shown in the tables. Bold numbers are most common oxidation state. The oxidation states shown in the parentheses are unstable. The +2 oxidation state in case of actinide very rare. Am2 positive has the electronic configuration 5f7. It is the analogous of European 2 positive piniums in the lanthanide but exists only in the solid state at the fluoride. AMF2 on the other hand, CF2, ES2F 2 positive, MF2, FM2 positive, MD2 positive, and NO2 positive exist as ion in solution. The properties of divalent actinide resemble more closely to Ba2 positive in group second. The most stable +2 oxidation state is exhibited by nobelium as NO2 positives and corresponding stable 5F14 arrangement. The +3 oxidation state is the most common oxidation state among all the actinide. However, this is not always the most stable oxidation state in the actinide. The first four elements THPA, U, and NP do not show +3 oxidation state as the most stable oxidation state. For example, U3 positive is readily oxidized in air as well as in solution. Interestingly, the most stable oxidation state of element up to uranium is the one involving all the valency electrons. Thus, the most stable oxidation state of a THPA and U are +4, +5, and +6 respectively. Although Neptunium show the oxidation state +7 by involving all its valence electrons, it is not the most stable state. This is because Np in +7 oxidation state is highly oxidizing and the most stable state is +5. The +6 oxidation state is exhibited by the old element from Theus have 90 atomic numbers. 2CF have 96 atomic number. However, Pa and Np display the most important +6 oxidation state, +4 oxidation state. The M4 ions are no in the acid solutions and are precipitation by F. PO4 3 negative and IO3 negative ions. The element older form dioxide MO2 and fluoride MF4. The plus 5 oxidation state is exhibited by the older element from Pa to Am. However, plus 5 oxidation state is more stable for Pa and Np. It is important to note that F, MF, M5 plus 5 ion do not occur in solution as such. In fact, these state occurs at their oxocations such as MO2 positive ions. A few solid compounds are known where in solution this proportion rapidly. The plus 6 oxidation state is exhibited by lower actinides in the form of their fluorides. Plus 6 oxidation state is more commonly found at the dioxo ions MO2 2 positive. The ions MO2 2 positive is linear and exists both in the solid as well as solution. One of the most commonly encountered compound of uranium is plus 6 oxidation state is uranyl nitrate dihydrate UO2 NO3 2 dot 2H2. It consists of linear UO2 positive ions surrounded by two NO3 negative ions and water molecule as shown. NO3 positive groups are bidentate and therefore two oxygen forms NO3 negatives are bonded to uranium. Oxygen atom from the two water molecules also bond to uranium. Thus, the coordinate numbers around uranium is 8. The UO2 positive unit is the compound UO2 NO32 H2O2 is perpendicular to a hexagon of 6 oxygen atoms, 4 from bidentate NO3 negative group and 2 from water molecules. The lower oxidation states are ionic while the higher oxidation states are increasingly covalent. The plus 7's oxidation state is known only in the oxycations of Np and Pu. When alkaline solutions are oxidized by O3, the important oxoanions known in case of Np and Pu are NPO4OH2 3 negative and PuO6 3 negative. 6. Color of the ions. Actinide ions are mostly colored. The colors of a particular actinide ion depend upon the number of electrons present in the 5f orbitals. The color of actinide ion arises mainly due to F transition. The color of characteristic cations formed by the actinide ions in aqueous solution. In addition to FF transitions in actinide, the colors can also arise due to FD transition as well as charge transfer transition. The color of the actinide ion solution because of FF transition occur in the visible and ultraviolet region. We have already encountered this FF type of transition in case of lanthanide as well since the F5F electron in case of actinide are projected out more in space than the 4F electron in lanthanideness. These 5F electrons are strongly influenced by the ligand field of ligand. This makes the absorption spectra of the actinide more complex compared to the straightforward spectra of lanthanide. A complex spectra is always different to characterize easily. It has been experimentally found that the absorption due to FF transition in case of actinide are nearly 10 times stronger and 2 times broader than the FF transition of lanthanoid ion. The energy difference between 5f and 6d orbital in case of actinides being smaller than 4f and 5d orbitals in case of lanthanoids. The actinoid ions inversely absorb light of lower frequency or higher wavelength. As a result, they allow and a very strong FD of transitions lie in ultraviolet regions and therefore do not influence the color of the actinide ion. It has been observed that the actinide ions in higher oxidation states display predominantly charge transfer spectra. This spectra is exhibited only by the high oxidation state ions which can easily oxidize the ligand. It is important to note that lanthanides do not exhibit charge transfer spectra because lanthanides do not display oxidation state higher than 4. Seventh, magnetic properties. The actinides show similar magnetic properties to lanthanides in terms of magnetic momentum with the number of unpaired electrons. This is shown clearly in figures where the magnetic momentums are plotted against the number of unpaired electrons. It is important to note that the high valence states have been fusions of 5f1, 5 F2, 5f3 and 5f4 ions which show the close similarities. Magnetic momentum values for the isoelectronic actinide ions are lower than the lanthanide ions. Example Np, Nce, Np5, Pr3, Np4 and Nd3. This is due to the fact that crystal field this is due to fact that 5f electrons in actinide are projected more in the space to the crystal field. As a result, the particle queen high of orbital occur by the crystal field effect. 8. Properties. Reactivity. The actinides are highly reactivity metals. This react with the dihydrogen and form non-stoichiometry hydrides with the formula MH2 or MH3. They react with hot water and tarnish in air, forming an oxide coating. The actinide react readily with HCl, but reaction with other acid is slower than expected. The metals are basic and do not react with sodium hydroxide. The actinide react directly with the halogen to form a variety of halide. The redox potential for known the M3 positives upon M couples are about minus 1.9 voltage. Thorium and uranium chemistry has been explored in detail. Some of general method for preparing compounds of actinide are given below. All the elements beyond actiniums in the periodic tables are radioactive. As a result, the nuclei of all the actinides are unstable and undergo radioactive decay. Among the actinides, uranium is the heaviest naturally occurring element with an abundance of 2.4 ppm in the Earth's crust. Among the actinides, TH and U occur on the Earth because the isotope of 235 atomic number have 92 mass number, 238 uranium 92, 232 thorium 90 and 244 Pu. Uranium. Since uranium is the most important of the actinoids, its chemistry will be discussed in more detail. The primary natural source of uranium is pinch, blind or uranite, which has the empirical formula U308. It is a mixed oxide containing uranium both in 4 and 6 oxidate state as UO2 to UO3. The other important ores are caronite, automonite, calcium caronite, extractions of uranium. As already mentioned, the main source of uranium is pinch blended. The detail of the extraction of uranium involves the following steps. First is concentration. The ore is crushed to a fine powders and its substance is subjected to conventionally greatly separation to remove the lightest impurities. Second is the roasting. The concentrations ore is roasting on the height of a rotary furnace in the presence of air to remove the volatile impurities such as sulfur, arsenic, and antimony. Acid treatment. The roaster ore is treated with dilute S2SO4 in the presence of an oxidizing agent such as MnO2 or NaClO3. This treatment converts uranium to soluble uranyl sulfate UO2SO4. The roaster ore can also be converted to a solution of UO2 NO32 by dissolving the ore in nitric acid. Fourth, treatment with ammonium carbonate. Adding of ammonium carbonate to above solution of uranyl sulfate precipitate it as ammonium uranyl carbonate. Alternately, ammonia is added to the solution of uranyl sulfate obtained in step 3rd acid treatment. This given rise to bright yellow precipitate of ammonium diuranate NH4 2U2O7. This precipitate is often called the yellow cake. This cake on heating gives rise to mixed oxide uranium 4 and uranium 6 oxides. Conversion into uranium dioxide. The mixture uranium oxide U3O8 is reduced to UO2 by heating either with charcoals or with hydrogen. 6. Production of uranium. Elemental uranium can be produced from uranium dioxide by using either of the two methods. First, UO2 is heated with vapor of HF to form uranium fluoride, which in turn reacts with magnesium to yield uranium metal. Second, by converting UO2 to a volatile uranium tetrachloride by heating it with elemental chlorine in the presence of charcoal, this is followed by reduction with elemental sodium. All the steps detailed above can be summarized in the flow sheet diagram for the extraction of uranium. Chemistry of separation of a neptunium Np, plutonium Pu, and americium Am from uranium. The three elements neptunium, plutonium, americium that follow uranium in the actinide series are produced mainly from uranium in the nuclear reactor. If you recall, uranium is the oldest known element among the actinides. Naturally occurring uranium contains two main isotopes, 238U92 and 235U92, which occur in the ratio 99.3% and 0.7% respectively. There is another isotope 233U92 which occur in trace only. Neptunium and plutonium, named after the planet Neptune and Pluto, were prepared for the first time in 1914 by a team of celebrated scientists by the bombarding uranium with neutrons in the cyclotron in Berkeley, USA. Both the elements are now obtained from spent uranium flue elements of nuclear reactors where they are formed by the capture of a neutron product in the fissions of U-235 uranium-92 fuel. Isotopes of plutonium Pu can also be prepared by reactions in which a fast neutron is added with the spectrum loss of two neutrons without allow timing for the intermediate product to decay. Americium can be obtained from the isotopes of plutonium by the success reaction in the nuclear reactor's edge. The yield of the heavier element after emission is controlled by the two factors. First is the half-life of the various isotopes and second by their ability to absorb neutrons. It is important to note that the stepwise addition of slow neutrons is very difficult. A quick method is to bombard the nucleus with a large number of fast neutrons without allowing time for the intermediate product to decay. For example, 238 uranium 92 add a fast neutron and then lose two neutrons to form an isotope of Neptune according to reaction. The separation of these elements from uranium is extremely difficult and hazardous. It is because these elements, including the starting material, are not only highly radioactive but also give highly radioactive fission products. Plutonium especially is extremely toxic. It does as small as 10 to the power minus 6 gram may be fatal, while smaller doses are carcinogenic. The separation of NP, Pu, and AM from U are based on following chemistry. First, stability of oxidation state. A steadily decrease in the stability of a high oxidation state with the increase in atomic number have been observed. With the increase in atomic number, the order of stability of the major ion involved are where the order in case of the oxygen ions is UO2 2 positives greater than NPO2 2 positive greater than PuO2 2 positive greater than AMO2 2 positive. Separation of these elements from uranium from fission product and from one another can thus be achieved by the adjusting the solution containing them to a suitable redox potential and them using solvent extraction or precipitation. For example, Pu can be oxidized to PuO2 positive while Am remain as Am3 positive. Thus, plutonium Pu can be removed by solvent extraction when americium can be precipitated as AmF3. Extraction ion. Second, extraction ion organic solvent. The MO2 positive ions from solution can be extracted into organic solvent. The M4 ions are extracted into tributyl phosphate in kerosene from 6MnH3 solution, where M3 positive ions are extracted from 10-16MnHO3. Third, precipitating reaction. Actinide in the +3 and +4 oxidation state can be precipitated as their fluorides or phosphate form acid solution. The higher oxidation state beyond +4 give either no precipitate or can be prevented from the precipitation by the complex formations with the sulfate ion. Fourth, ion exchange method. Ion exchange methods are commonly used in separation for small amount of materials, as in the separation of americium Am. Spent uranium fuels road removed from the nuclear reactors can be used to extra NP and Pu in kilogram quantities, where Am is 100 gram quantity. The reprocessing of the nuclear fuel road is an important technology, as these help to extract new elements that may be used as nuclear fuel. Spent fuel rods are dipped in ponds of water for several days to allow them to cool. During this dipping period, the intensely radioactive isotopes with short half-life such as 5153I half-life is 8.04 days lose most of their activity. The fuel rods are dissolved in 7MHNO3 and extracted with the 30% tributyl phosphate in kerosene. The extraction coefficient of the actinides in 7HN3 solution containing 30% tributyl phosphate in kerosene are the MS3 positive ions have very low extraction coefficient is 7 NHNO3. As a result, nitrates of UO2 positive and PU4 positive are probably extraction in tributyl phosphate, leaving the others actinide namely NP and AM along with the other fusion product in aqueous solution. It is also important to note that 7NHO3 cannot oxidize Pu4 positive to higher oxidation state. Pu5 and Pu6 reductions of UO2 positives plus Pu4 positives nitrate solution with SO2. NH4OH or Fe NH2SO42 gives aqueous solution of Pu positive 3 without affecting the reduction of UO2 positive. Thus, Pu4 positive is reduced to Pu3 positive which enters the aqueous phase while UO2 positive remains unchanged in organic layer. UO2 positive species present in kerosene oils on treatment with 0.2 NH NO3 gives UO2 NO32 in aqueous solution, which on evaporating leaves a solid's mass of composition UO2 NO32 dose 6H2O. On heating this hydrate solids compound to 400 degrees Celsius gives UO3, which upon further reduction yields UO2. On the other hand, aqueous solution of reduced Pu3 solution on treatment with nitrous acid get oxidized to Pu. This solution reacts with oxalic acid to give crystalline precipitate of the composition Pu C2O42.6H2. Heating the hydrate compound to 300 degrees Celsius gives PuO2. The whole sequence of the steps outlined in the process are described. The separation of other actinides, namely NP and AM, can be achieved by the use of approximate oxidation reduction cyclic couples with the solvent extraction. For example, Pu3 positives are in aqueous nitric acid can be oxidized to PuO2 positive by an oxidizing couple with E E0 greater than 1.02 volt, following by the extraction into hexane where Am3 positive is uncharged and remains in aqueous solution. Transuranic element with an atomic number greater than 92 are called transuranic element. Before the Second World War, the elements were thorium, protactinium, and uranium were located below hafnium, tantalum, and tangents in the periodic table. The synthesis of neptunium in new element with atomic number 93 by the Millians and abolition in 1940 was demonstrated by the bomb-bearing uranium with neutron. This newly discovered element should be postenoid immediately to the right of a tangent below rhenium. However, the property of neptunium resembles more with uranium rather than selenium. It was the discovery of neptunium, followed by the subsequent system of a new element that was responsible for the new series of elements called the actinide series. All the transuranic elements are radioactive in the nature and have short half-life period. Neptunium, plutonium, and americium were unknown prior to their synthetic preparation by nuclear reaction. However, these elements were later found to be present in trace quantities in uranium's ore, synthesis route to transuranic element. Transgenic element. There are two synthesis routes which are commonly used for the synthesis of transuranic element. A neutron may be captured by the nucleus with the emission of a gamma ray reaction. The neutrons increase the mass number of the nucleus by 1 unit and some energy released as by gamma radiation. Further, neutrons may be added in a similar way. Addition of neutrons increase the neutrons to protons ratio. And this makes the nucleus unstable because it contains too many neutrons. As a result, the nuclear decay by converting in neutrons into a protons and alpha beta particle. This reduces the N upon P ratio and also increases the atomic number by 1. Thus, a new element is formed. The other method involves the capture of small ions by the heavy nuclear. This is possible only if the bomb-boring particle have sufficient energy to overcome the Coulombic repulsion between the ion and the heavy nuclear. The smaller ions are accelerated in a linear accelerator or cyclotron to possess sufficient kinetic energy. The simplest ions using in the alpha particle, this increase the atomic mass unit by several units and the atomic number by 2 units. Synthesis and the transchronic element. All the transchronic elements have been present by the nuclear reactions which involve bombardment with either the neutrons, alpha particles, or the other small nuclei. Preparation of neptunium. It was prepared by M.C. Million and abolitionists in 1940 at Berkeley by the bombardings with slow neutrons. Hence 239U92 was obtained. 239U92 being unstable emit beta particles and result in the formation of neptunium after the name of the planet Neptune. Preparation of plutonium. It was discovered by the Seaborg and his colleagues during the beta decay of neptunium 239. Plutonium was named after the name of the planet Pluto. Preparation of americium. Americium was synthesized by the bomb-bearing 238 uranium 92 with alpha particles. Preparation of curium. Curium was synthesized by the bomb-bearing 239 Pu 94 with alpha particle. Preparation of beryllium. Beryllium was synthesized by the Seaborg and his colleagues by the bombarding americium 241 with high speed of alpha particles. Preparation of californium. Californium was synthesized by bombarding curium 242 with alpha particle. Preparation of actinium. Actinium was synthesized by the bombarding U-238 nucleus with accelerate nitrogen nuclei. 2 isotopes of californium have been identified. It can be also prepared by the bombarding isotopes of californium 250 with the neutron californium 253 obtained during bombardment process result in beta decay forming actinium. Preparation of a fermium. Fermium was synthesized by the bombarding actinium-253 with neutrons. Preparation of a mendelium. Mendelium was synthesized by the bombarding actinium-253 with alpha particles. Preparation of a nobelium. Nobelium was synthesized by the bombarding curium-246 with actylate stripping carbon 6 positives. Preparation of a lawrecium. Lawrecium was synthesized by the bombarding californium 250 with actylate boron nucleus. A summary of synthesis of transcurionic element along with the half-life of element in given tables. The latest or heavier actinide element. The element from curium onward, namely curium, beryllium, californium, xanthium, ferrimium, magnesium, nobelicium, and lawrecium are named as later actinide. Very little is known about the chemistry of these later actinides because of their limited availability and extreme instability. The availability of some of the most assembly isotopes are. It is clear from the table that curium is available only in macroscopic quantities, where the later actinides above atomic number Hanger have been prepared only in minute quantities. In other words, later actinides are available in trace amount. It is interesting to note that the later actinides show close resemblance to the lactinide. However, the actinide can be easily separated from the lactinide because of the actinide readily formed complex. For example, the actinide reacts with contraction HCl to form the corresponding chloro complex. If both groups be eluted more conventionally with the contraction HCl after eluting the actinide can be represented separate from each other by ion exchange using citrate solution to elute them. It is interesting to note that the order in which the positive actinide ions are eluted show a close similar to the order in which the tripositive lanthanide ions are eluted. Display the eluting diagram for the actinide and the lanthanide element. The first identification of the element from americium to metallium on a weightable scale was made through elution. All the actinides with atomic numbers 96 angle 3 Cm, Bk, Cf, Es, Fm, Md, No, and Lw, with the exception of nobelium, have plus 3 as the most stable oxidation state. The most stable oxidation state of nobelium is plus 2. This is because it has the most favorable F14 electronic configuration. Actinide with atomic number 98 to 1 angle 2 clariformium to nobeliums also display plus 2 oxidation state, except of nobelium plus 2 oxidation state is strongly reducing in nature. Higher oxidation state of a curium Cm plus 4 are found in the solid state in compounds such as CmF4 and RbCmF5. Similarly, beryllium compounds are stable in the plus 4 oxidation states such as BkO2 and Cs2BkCl6. Lawrecium oxides only in the plus 3 oxidation state and resists oxidation and reduction. This resistance of oxidation plus 4 and reduction plus 2 illustrates the stability of an F14 electronic configuration. The element up to atomic number Hanger undergo radioactive decay mainly by the emitting alpha particle or beta particle. The latter element become increasingly unstable as the atomic number increases. Nobelium is extremely unstable and has a half-life of only 3 seconds. Element beyond Z is equal to 1 angle 3. The actinide series is complete and lawrenium. So we have already learned that the half-life of a latter actinide beyond atomic number, hunger decreased considerably. For example, the half-life of inobilium is only 3 seconds. It has been calculated that the half-life of element will decrease further as new elements are discovered. The half-life of an element with an atomic number 108 is expected to be very short, about 10 to the power minus 4 to 10 to the power minus 6 seconds due to spontaneous decay. As a result, it is extremely difficult to synthesize and study the chemistry of elements beyond 108. However, these difficulties have not impeded the spirit of the scientists, and they have been successful in discovering elements up to atomic number 112. Out of 112 known elements, elements up to atomic number 109 have so far been named. A major controversy come to light over naming the element. The choice of the name of element belong to the discovery. In the case of postanoids, three nuclear facilities are in competition for the synthesis of each of now newly discovered element. The facilities are at Berkeley, California, Dubna, Russia, and Darmstadt, Germany. It is extremely difficult to identify which nuclear facilities had the true claim. For example, the discovery of element 104 was claimed by both Berkeley, USA and Dubna, Russia group. The American named the element Rutherfordium after Ernest Rutherford, while the Russian named it Kurchatovium after Igor Kurchatov. While these conflicting claims were being settled, the International Union of Pure and Applied Chemistry devised a hybrid Latin Greek numerical system of providing provisionally name and symbol to all the newly discovered elements. The name of derived directly from the atomic number using root for the their digit in the atomic numbers of the element and adding to the ending IUM the root of for the number and their abbreviative R. In some cases, the names are shortened by the removing the repetitive letter. Example, Bi plus IUM can be written as broom, or tri plus IUM can be written in short form trium. Let us name an element with atomic number 106 according to hybrid Latin Greek nomenclature. The name of the element is derived by combining together the root in the other of digit, which makes up to the atomic number, followed by adding IUM in the end. The symbol for the element Unix with atomic number 106 in UNH. Similarly, the name and the symbol of the element with the atomic number 102 can be worked out. The IPSC names for the element with atomic number more than hanger are given below. The newly recombined name for the element with atomic number 104 to 109 are also mentioned. Comparisons of actinides and lanthanides. Both lanthanide and actinide consist element of F block, as these involve the gradual filling of F orbitals. These elements occupy a distinct safe space at the bottom of periodic table. They show close balance in some of their properties, but also differ in many properties. Let us review some of important points of similarities and difference among of lanthanide and actinide. Point of similarities. Both the lanthanide and actinide involve the filling of a f orbital. Both the lanthanide and actinide display predominantly the plus 3 oxidation state in most of their compound. Third, due to pure shielding of the 4f and 5 electrons, both the lanthanide and actinide show greatly contraction in size of their atom with the increase in atomic number known as lanthanide and actinide contraction respectively. Electrons of lanthanide and actinides with the same number of unpaired electrons display similar absorption spectra due to FF transition. Fifth, lanthanide and actinide are highly electropositive and are very reactive. 6. Nitrate, sulfate, and prechlorate of trivalent lanthanide and actinide are soluble in waters. Hydroxide, fluoride are carbonate of trivalent lanthanide and actinide are insoluble in water. 8. Both lanthanide and actinide can be separated by ionic charge method. Point of difference. The most point of difference between the lanthanide and actinide are present in table. Properties. First, metal orbital. Lanthanide. It involves filling of 4f orbital. Actinides. It involves filling of 5f orbital. Energy gap between f and d orbitals. The energy gap between 4f and 5d orbital in lanthanide is very less. As a result, their chemistry is fairly similar. The energy gap between 5f 6d in anthanide is small. As a result, their chemistry is very different. Binding energy of 4f orbital are higher in lanthanide and lower in actinoid. Oxidation state. The most common oxidation state is plus 3 in the addition to some lanthanide showing plus 2 and plus 4 and some addition actinide show plus 2 plus 4 plus 5 and plus 6. Shielding effect. 4f electron exert greater shielding effect. 5f electron exert pure shielding effect in anthanoid. Ability to form oxyanion. Lanthanoid do not form oxocations. Actinides form oxocation higher oxidation state. UO2 2 positive, UO2 positive, NPO2 positive, PuO2 positive. Color of the ions. Most of lanthanide ions are colorless. Most of actinide ions are colored. Example, U3 positive have red, U4 positive have green, and UO2 positive have yellow. Complexing ability. The tendency to form complex ability is small in lanthanoids and the tendency to form complex is large. They do not in actinoids and they do not form complex with pi bonding ligand. Radioactivity. All the lanthanide except prometinium are not radioactive. All the actinides are radioactive. Coordination number. Lanthanide display coordination number 6, 7, 8 and 9 and actinide display higher coordinate number 8, 9 and 12. Basic character. Compounds of lanthanoid are less basic in character. Compounds of actinides are more basic in character. Thank you.